Hello ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. This is lecture 5, Important Mathematical Elements in the Riemannian Geometry. We will talk about the Christoffel symbols, the geodesic equation, the Riemannian curvature tensor, the Ricci tensor and the curvature scalar. Now we want to introduce the Christoffel symbols. We consider the case of a free particle and we need then the Lagrange function for a free particle. From classical mechanics we know that the Lagrange function is given by the kinetic energy. That means L is equal to a half mass and the square of the velocity. But now we have to generalize the whole formalism for curved spaces. So we begin with the line element 162. We know from a former lecture here that ds squared is given by metric tensor G and the differentials of the coordinates. ds squared is a scalar, and so here we have two scalar products. Then we need the velocity. Velocity is ds dt, that's clear. And that means for v squared we have ds dt squared, and that means we have here dx dt here in the equation 163. We use in the four-dimensional space the Greek indices. Then we get for the Lagrange function half mv squared. Then we substitute 163 for v squared, and then we want to use some abbreviations to have less to write. For the time derivative we use a dot x dot, and for the partial derivative here with respect to the coordinates we use this absolute value sign with the index or this version here. You have to recognize that contravariant index in the denominator is a covariant index in the numerator. That should be known from the elementary lectures in theoretical physics, from classical mechanics here. If we have the action integral, means integral over the Lagrange function, and we make a variation calculation, then we get the Euler-Lagrange equations for motion. Here we again have to generalize everything, and we now in a four-dimensional space-time continuum, and so we have four coordinates instead of three here like in classical mechanics. We write for the action integral, another L now here, and we have of course as the independent coordinates the coordinates and the velocities. And now we use a parameter s instead of time, because time is the fourth coordinate here now. We have a parameter s, that is the length of the trajectory of the body. And then we get, analogously here, the Euler-Lagrange equations for the four-dimensional case here in curved spaces. 167. This is an exercise for students. Derive the Euler-Lagrange equations here in this case. Now we need the derivatives, and though we consider first the derivation with respect to the coordinates. Yeah, the velocities are independent coordinates. They do not depend on the coordinates. So the only dependent quantity of the coordinates is g. And so we get for dl dx alpha here, yeah, this expression with the derivative of g. And yeah, written now here with the parameter s. We have this here in the four-dimensional case. Then the other derivatives here, we have to differentiate with respect to the velocities. And yeah, we have two velocity factors here in 168. That means if we differentiate, we will get two dents here. So, yeah, we have here in the differential quotient the index alpha, and here we have the indices mu and nu. If we now differentiate, we get for the first term here a Kronecker delta with mu and alpha, because we get only value 1 if mu and alpha are identical. And the other differential quotient stays as a constant factor here. And in the second part here, we have delta mu alpha, and the differential quotient with mu is, we can say, a constant factor here if we differentiate. Then we can eliminate the Kronecker deltas, because we have here a scalar product with a metric tensor, and so the metric tensor overtakes the index alpha instead of mu here. And in the other term here, we have then mu alpha. Then we have in the term here scalar product, and so it makes no difference which index we use for such a scalar product. So we rename this with the index mu. So we have twice the same term here, and so we have factor 2, which is cancelling with a half here, and so we get m metric tensor and differential quotient xs here. Okay, then we substitute the expressions here in 167 in the Euler-Lagrange equations, and then we get this 170. Okay, now we have to differentiate here the term in the parentheses. We have two factors. So here in the first dent, we have differentiated the differential quotient xs here, and here in the second dent we have differentiated g, the metric tensor, okay, according to the product rule of differentiation. The second term here stays like above. Then we want to have g here with a differentiation to a normal coordinate. So we use the chain rule of differentiation, and we write then here differentiation with respect to nu, and here we have the additional differential quotient dx nu ds. then we factor out the metric tensor G. So we then have here 1 G and here a half G, and so we split this G in two half G's. So we can write this here, the parenthesis with 3 derivatives of the metric tensor. Then we have here a symmetry in the indices mu and nu. And so we change in the first ident the two indices. And so we have now this equation 174. And now we multiply by a contravariant metric tensor G alpha beta, so that we haven't got here a metric tensor in the first term. Yeah, here we would get a Kronecker delta with mu and beta, and so this mu here becomes a beta. Okay, so we have 175 then, and now we use another symbol for the term with the metric tensors here. We use a capital Greek gamma for the sum of the 3 metric tensors here and the factor a half. And these are called the Christoffel symbols of the first kind. Or there is another notation with brackets here. This is found in older literature, I would say. We will use the capital gamma here in our lecture series. The indices we see here at gamma, or here in the brackets, it's the order of the minus G here. Mu, nu, alpha. Mu, nu, alpha, and here in the brackets, mu, nu, alpha. Okay. Then, if we multiply this contravariant G tensor here in 175 to the Christoffel symbol of the first kind, then obviously we have then, instead of 3 covariant indices, we have 1 contravariant index at the gamma here. And then we have here an additional G tensor in this expression, and this is called now a Christoffel symbol of the second kind. Or here we find, especially in older literature, another notation with the braces here. Beta, mu, mu. And because of the symmetry of G, there is a symmetry of the 2 covariant indices here of gamma. Means here 178, that is true. And now we can substitute in the Euler-Lagrange equation the expression with the metric tensors by using a Christoffel symbol of second kind. If we only talk about Christoffel symbols, we usually mean the Christoffel symbols of second kind. We seldom use the Christoffel symbols of the first kind, I would say. Okay. And then if we substitute now here, we get this equation 179. This is the so-called geodesic equation. It is the equation of motion for a free particle in a curved Riemannian space. Now we want to know how we have to transform the Christoffel symbols from one coordinate system into another one. And here the Christoffel symbols have 3 indices, but we have seen that Christoffel symbol is no tensor, and so we must be careful with the indices. We cannot apply the metric tensors to make out of lower index upper index, or vice versa. Here we must be careful. Now here we have in 180 the definition of a Christoffel symbol of the first kind, and we want to write the differential operator separately from the metric tensor, and so we use the transformation law for a tensor. G is a tensor, here is G prime, and so we write G of the unprimed coordinate system with a transformation here. The 2 indices means we get 2 differential quotients, and and we make this for the 3 indents here, so we get 181. And now we apply again the product rule of differentiation, and so we get this expression here, because we have here 2 factors, we can say, and the differential operator here is applied to this product of the differential quotients and G. And so we get here always an addend with the differential quotient G here, and we get here an addend with only the differential quotient and the differential operator, where we can factor out G. Okay, this is 182. Then we apply the chain rule again, because the metric tensor is differentiated with respect to different x vectors. So we use this rule here again and factor out then dg dx beta here in the first line. So we get this. And then in the second line, we have factored out here the parentheses. We have here 2 factors, and if we differentiate, then we get 4 addends here. So we have here 6 addends here in the second line, 183. And now we want to factor out here the 3 differential quotients. And we can do that by renaming some indices. We have scalar products, and for a scalar product we can use any index. So in the second term we exchange beta and sigma. We have here beta here and beta here. That is a scalar product. And sigma are here covariant and here contravariant. So we exchange these 2 indices. In the third term we rename rho by sigma, sigma by beta, and beta by rho. And so we have 3 times the same term, and so we can factor out the 3 differential quotients. Okay, we have changed the indices. That means we have now different indices here in the G tensors. Okay. Then here in the second line of 183, if we compare the terms, we find that here the third term is identical to the fifth term here. And this is minus and this is plus, so we can cancel them out. And then we have a symmetry in the indices rho and sigma are here in the first and in the last term. Then we have then the same terms, so we can cancel them out as well. And though we have only two tens here in the second part of the equation here, 184. We can now write here for the sum of the derivatives of the metric tensor. Again, the Christoffel symbol. That's the definition of a Christoffel symbol. And here in the second part, we see that the two terms are identical because the order of differentiation makes no difference. So here we have mu and here we have mu. That's the same. And so we get a factor 2 is cancelled by a half here, and so we get here 185. And now we multiply again by a contravariant G tensor to get the Christoffel symbols of the second kind here. So we get here gamma prime with a contravariant lambda. So we have 185 and 186 for the Christoffel symbol of first and second kind. This is a transformation law. So, and yes, we see now if we had only the first term here in the equations, then we would have the transformation law of a tensor. But here we have an additional dent here in the two equations here and here. And though because of this additional term, obviously the Christoffel symbols do not transform like a tensor. So Christoffel symbols are no tensors. Now we consider the transformation of the partial derivatives of a tensor T. We consider a tensor of first rank with one index alpha here. So we can write here differential quotient, or we can use this writing here. And then we get the tensor in the unprimed coordinate system by transforming the primed tensor in the primed coordinate system with the normal transformation rule here. Then we solve the parentheses here, and then we use the chain rule again. It means instead of dt dx gamma, we write here dx x delta x gamma, and then we have a x delta here in the differential quotient with t. And here similar, we differentiate the differential quotient and then write another differential quotient by using the chain rule here. Okay. So this is now obviously the transformation of a tensor here, a derivative of a tensor. And that looks similar to the transformation of the Christoffel symbols, but also two terms. But here now we have a problem. Christoffel symbols are now tensors, but here we have a tensor. And the derivatives of a tensor must transform like a tensor. That means, we do not need such an additional term here. So, how can this problem be solved? We first substitute the Christoffel symbols. We use the transformation law for the Christoffel symbols and substitute that in equation 187 here. And so we get now 189. First we have resolved the expression for the Christoffel symbols for this differential quotient here. Okay. Then we have this expression here, 189. And now we solve the parenthesis here and set another parenthesis. Here we have the first term, two differential quotients, and the derivative of the tensor t. And we have the same if we take here in the second part here the t, here it's a differential quotient, the same like here. And so together with that Christoffel symbol here, we have the same differential quotient, and so we can factor out the two differential quotients, and then we have in the new parenthesis here this sum. And then here in the negative term here, that is here the other part, we have here this multiplied by this, and we can here cancel out two differential quotients. That means here we have dx lambda, and here dx delta and dx delta in the numerator, denominator. So we cancel that out, and we have only this expression here, 190. So for the second term here, we can write this, because this is the transformation law for the tensor, and here we have the primed tensor, and so here we have the unprimed tensor. Then we obtain for 190 this expression. If we write for the second term this term, and we write it to the left side of the equation here, we have this, and and the right side here, all the things here are remaining here. Okay, so and what we have here now is exactly what we want to have. We have here a tensor, and here we have the two differential quotient for the transformation, and no additional term here. And so we call such an expression here in parentheses now the covariant derivative. So that means we have not only a differential quotient if we want to differentiate a tensor. We have an additional term with a Christoffel symbol, the second kind. We write for the covariant derivative here a capital D. Sometimes, in other literature you find a Nabla operator to write down the covariant derivative. And so we must substitute the normal derivative by the covariant one here. Means instead of this first derivative of a tensor, we write capital D. And then the capital D means we have the normal differential quotient plus the term with the Christoffel symbol here. Or another writing, Nabla operator. Or we find in other literature a semicolon and the index. Or another kind to write the covariant derivative is a double absolute value sign with the index. And analogously we have for the covariant vector. That's the vector, it's a tensor of first rank. We can write here the same. Okay, Christoffel symbols are now tensors, and if we look at here this formalism here, the Christoffel symbols are also called transition coefficients. The upper index of the Christoffel symbols of second kind stands for the component of the change of basis vectors, while the parallel shift along the basis vector, another basis vector, and the covariant derivative of a scalar function phi reduces to the normal usual derivative, means capital D and partial D, then that's the same for scalar function. Another word to the covariant derivative. In quantum field theory, gauge theory, the covariant derivative is introduced. Keep the transformation invariance in the formalism. And so electromagnetism, we introduce the gauge field, the photon field, with the covariant derivative. Or another famous example is the theory predicted the W and Z bosons for the weak interaction. And later they were found in the European Nuclear Exploration Center, CERN, V and Z bosons. So the covariant derivative is very important in physics. Now we want to introduce the Riemannian curvature tensor. We consider now the curvature directly. You should have learned curve sketching within calculus in school, and there you have worked with curves y which depend only on one variable x, and if the curve switches over from a left band to a right band or vice versa, then the second derivative would vanish at such an inflection point. So the second derivative is a measure for the curvature. But now we have a higher dimensional space. We have 4 coordinates. So we have to generalize the formalism again. We consider a vector field, V, and then we use, of course, the covariant derivative. So we write down here the second derivative of the vector field V. So here in 200 we carry out the first covariant derivative d alpha. That means we have here one partial normal derivative, and because we have 2 indices beta and gamma here, that means we get here 2 terms with the Christoffel symbol. Yeah, that's according to the definition of the covariant derivative. Then in the next line, 201, we carry out the second covariant derivative. So we get here this result. And then we write down the same equation again, but we exchange the 2 indices alpha and beta. And so we get this equation here, 202. Now we subtract 202 from 201. So yeah, we get this result here, 203. Yeah, these are all the terms from above here in this equation. But now we can cancel out some terms. The first 2 terms here, we have only partial derivatives, and the order of the partial derivatives makes no difference. So this term is the same like this term. Okay, we have plus and minus, so we can cancel these 2 out. Then the next 2 terms, yeah, these are the first 2 terms here. They stay in the equation. Then the next 2 terms here, yeah, we have a symmetry in the lower indices in the Christoffel symbol, so beta alpha, that's the same like alpha beta, and yeah, all the other indices are the same. So these 2 terms cancel out again. You have here plus and here minus. And then the next 2 terms here in the other line, that's the same situation. Beta alpha in the Christoffel symbol, that's the same like alpha beta. All the other indices are the same, and we have plus and minus. These 2 cancel out. The other 4 terms here, they stay in the equation. So we have now this equation 204. Now we want to factor out a V mu, the vector field. So the first 2 terms, we have got them here. This is the first one, and this is here the second one here in 205. And then, yeah, here these 2 in terms, can cancel them out because there is a symmetry between alpha and beta. If we exchange alpha and beta, then yeah, we would only change perhaps the sign, but we have minus plus, and it makes no difference whether we have minus plus or plus minus, we can cancel them out. And so we have still the 2 remaining terms, which we find here in 205, and we have factored out V mu. Okay, so the expression here in the parentheses has nothing to do with the given value. And so we use for this expression an abbreviation R, yeah, with 4 indices. And yeah, this tensor R is called the Riemannian curvature tensor. Okay. Yeah, it's a tensor of fourth rank. And it is, we can say, the second derivative of a vector field, and so a measure for the curvature. Yeah, here we should recognize, if we consider the metric tensor, especially with curvilinear coordinates, then we cannot decide whether the space is curved or uncurved. But if we consider the Riemannian curvature tensor, if we have a point or a region of no curvature, then the Riemannian curvature tensor would vanish. Okay? And yeah, we also can apply the Riemannian tensor to higher rank tensors. And then we would obtain for each index an expression like in 203. Okay. And for example, if we consider a tensor of fourth rank, here we have two covariant and two contravariant indices, then we can firstly write this 4 terms with R. And if we want to carry out further calculations, then we must substitute R 4 times here with such an expression here, 206. Okay. Then the Riemannian curvature tensor has got some symmetry properties. But first we consider the tensor with 4 covariant indices. Yeah, that's no problem. We know we can change a contravariant index into a covariant one by using the metric tensor. And so we can consider now the symmetry. And if we interchange the first two indices, here nu and gamma, to gamma and nu, then we would have an anti-symmetry. That means we have a minus here in R. Okay. And the same have we got in the two last indices here, beta alpha and alpha beta. There's also an anti-symmetry in the last two indices. Okay. And then if we interchange the first two and the last two pairwise, here 211, then we would see there is a normal symmetry. Okay. And then there is an additional condition for the Riemannian curvature tensor. It is called the Bianchi identity. If we write down here the sum of 3 covariant derivatives, then we have as a result 0. Yeah, here we look at the indices perhaps. Here in the first D we have an index row, and we find the index here in the next term as a third index. Here we have D nu, and we find nu here in the next term as a third index. And here we have D mu, we find mu as a third index here in the first term. Okay, Bianchi identity. Yeah, this is an exercise for students. Show that these equations for the symmetry are correct. That's very easy. You must only use the definition of the curvature tensor and substitute then a short calculation, and then you will see, these symmetries are true. Then if we want to know how many independent components have we got in R, then, okay, we have a four-dimensional space, we have four indices, that makes 4 exponent 4, altogether 256 components in that tensor. But there are only 20 independent ones because of the symmetries. How can we calculate that? Okay, yeah, because of the symmetry in the first two indices, we have only 6 independent components. And because of the antisymmetry in the last two indices, we have also got 6 independent components. So that means we have 6 times 7 combinations. That makes 42. But because of the symmetry of the last two and the first two indices, we must divide by 2. And so we have 6 times 7 divided by 2 makes 21. And then we have still got the Bianchi identity as the last condition here. So we have to reduce that to 20. That means, yeah, the Riemannian curvature tensor has only got 20 independent components. Now, the next we have is a Ricci tensor. Yeah, we can execute a scalar product in a scalar product with a Riemannian curvature tensor. Yeah, the only possibility that makes sense here to carry out an inner scalar product, that is if we use one of the first two indices as a covariant index perhaps, and one of the last two indices as a covariant index. And so we have here a scalar product within the Riemannian tensor, and so we have only 2 indices then. Yeah, and this is called the Ricci tensor. And we can write for the Ricci tensor, this. That is the definition for the Riemannian tensor, but we have exchanged an index. So that means we have here in each addend here an upper and a lower mu. Okay. And because we had a symmetry in the first two and with the last two indices, and here we have this is one index of the first two and one index of the last two, and so we have a normal symmetry in the two indices of the Ricci tensor. R mu mu is the same like R mu mu. Okay, and then of course it is possible to carry out another scalar product. Okay, that means we use here the metric tensor G to get one contravariant index here in the Ricci tensor. So we have here mu, mu, co and contravariant. That means another scalar product with 4 terms. And so we get a scalar R, and this is called the curvature scalar. We can interpret the curvature scalar with the kind of curvature radius at every point in space. Now we finished lecture 5. Next time we will talk about the Einsteinian field equations and how Einstein found them by a very long procedure of trial and error. Thank you for watching. See you next time. Goodbye.